Again, thanks very much to the organizers for inviting a talk from the CMBS4 project. So we've heard a number of talks about the cosmic microwave background, and I think that's a testament to the vast array of physics that you can get out of the cosmic microwave background. You're basically getting an imprint of pretty much the entire history of the universe. So it's not only looking at inflation, not only looking at recombination, not only looking at the current universe, but you're really getting everything all along the way. And that's one of the reasons why it's such an exciting probe. We've, of course, already heard very much about the different types of power spectra. You're not getting a single number. You're not even getting a single spectrum, but you get the temperature spectrum. You get two types of polarization spectra, the E modes, which are mostly the scalar density perturbations, and then the B modes, which are a combination of the scalar polarization and the tensor, that is the gravitational wave signals. Depending on the angular scale you're looking at, different types of physics will dominate. And so we're, oops, nope. Yeah. Everyone has trouble with getting their fingers to remember which button to look at. Okay, there we go. So on the very large angular scales, the low multiples, then we can go after the earliest parts of the universe, the inflation signals. In the middle parts, we are seeing the matter mapping, basically, the gravitational lensing that's going on, and effects of things like neutrino mass. And then on the damping tail, we start to get into light relics and other very interesting physics that's going on. You can see that the sizes of the error bars are really improving dramatically over time. We really have the temperature nailed down already. The E modes are getting there. And of course, the B modes are things that the next generation of experiments is focusing on. Oh, should go back. So on the, what we're also doing is we're making a general map over this range of frequency, these sub-millimeter and millimeter wavelengths of the universe, and in particular of our galaxy. And so you will get from CMBS4, you'll get the deepest millimeter map of all the astrophysics that's going on in the millimeter wavelengths with polarization. And transients as well. I'll talk a little bit about that. So as one of the key science drivers, you have looking for those primordial gravitational waves from inflation, which is really one of the unique signatures of inflation. We have many evidences for inflation and so forth, but those gravitational waves will really nail things down. And we talk about that, as you've heard, in terms of this tensor to scalar ratio of R. And you also have the scalar tilt to the power spectrum, NS, so this R-NS plane. And there are many different theoretical models. As we've heard about in the last couple of days, the initially favored monomial models in the dark blue bands here really are pretty much lying outside of current constraints. And so theorists have many other models that they can look at and motivate, of course. And a limit that one can get from CMBS4 will then be down in this red region, much smaller than the current limits. And then, of course, we can also hope for an actual detection. And this bottom plot shows the ability that you have to actually zero in on a particular model of inflation. Here it's Higgs inflation and Starobinsky inflation in this region. So you'll be, if that's the true inflationary model, we'll be able to pull it off of zero. We'll be able to detect the gravitational waves, and we'll be able to constrain it fairly well as well. So CMBS4 is aiming to reach the uncertainty of 5 × 10⁻⁴. So quite a bit lower than current constraints. And this is done by dramatically increasing the instrumentation, the number of detectors you have, up to 500,000 detectors. One can also look at the more physics in the early universe, in particular the light relics. You can talk about this in terms of the number of species that you have? Is it just three neutrinos, three light neutrinos, or are there further light degrees of freedom? So is N effective near 3, or is it off from 3? And again, we'll be able to do about a factor of 6 improvement over current in the uncertainty on measuring those number of light degrees of freedom. But one's really mapping the dark sector even more beyond just the number of species. You can see there's a vast array of signatures you can get from isocurvature, from axions, from dark matter annihilation, and so forth. So you're probing this enormous range of dark matter masses, all through everything from the primary CMB to CMB lensing to features such as oscillations, modulations in the CMB. And so there's just a wonderful array of physics that one can go after. In mapping the matter, we've heard a number of talks about the CMB lensing. And again, that's incredibly important, but there are many, many other signatures. And so at the bottom here, you can see the CMB lensing, but you also have the various Sachs-Wolf effects, looking for voids, for example, the various different types of Sunyaev-Zeldovich effects, looking for the electron density, looking point sources, clusters, infrared background, galactic emission, and so forth. So there's again, this cornucopia of different physics that one can go after. One also looks for cross correlations with the density surveys, the galaxy surveys, but the imaging surveys, such as one gets from Rubin Observatory and from Euclid, and the spectroscopic surveys such as DESI. You cross-correlate the CMB information and the galaxy information to make sure you're seeing the same physics and astrophysics from them both. And this also gives you a lot of complementarity in the neutrino mass with the laboratory experiments looking at neutrino oscillations to measure the neutrino mass as well. As I mentioned, one's also making a general map of the millimeter sky. And because you repeatedly scan the sky, you're basically doing a time domain experiment in the millimeter region as well, just like the Rubin Observatory is doing it in the optical. And so you can look for transients such as tidal disruption events, gamma ray bursts, effects in the millimeter, and so forth. And so it's really a multi-messenger astronomy that you're seeing, not only in the optical, but you're bringing it into the millimeter regime. And so there'll be all sorts of new discoveries that we have not yet thought of. So talk a little bit about the design. The key aspects of it are an ultra deep survey, which is mostly going after the inflation science, and then a very deep and wide survey going after the matter mapping, the light relics, and so forth. So we use 2 sites, planning on using 2 sites, the South Pole and the Atacama Desert in Chile, and using both large aperture and small aperture telescopes, again, to go after the wide range of different science cases that you have. Using 7 frequency bands over a broad range from 20 to 300 gigahertz. And again, the technology already exists. It's just a matter of dramatically scaling it up by about a factor of 10 in the number of detector channels that one has. And so, of course, it takes a lot of work to do that, but there's nothing that we don't know how to do. It's just a question of getting the time and the resources to actually scale things up dramatically. To talk in a bit more detail about the telescopes, there'll be 2 of these large aperture telescopes in Chile to do this deep and wide survey. And again, you have this wonderful overlap with optical surveys such as DESI and Rubin, and eventually the Roman Space Telescope as well. The technical design for these is a cross-Dracon design. Here's the angular resolutions that you get. And again, this is something that we know how to do, how to build, basically. There's a lot of experience from existing telescopes, such as from FIST and from the Simons Observatory. At the South Pole, there are both large and small aperture telescopes. The small aperture telescopes are really drilling down in a smaller region of sky to great sensitivity, going after the B-mode survey, building on what we've heard of already with the BICEP Keck array and the South Pole telescope, going after the large area surveys for delensing in conjunction with the Chilean large aperture telescopes. So there's been a lot of advances in improving and reducing systematics, things like gapless mirrors, so you don't worry quite as much of some of the scattering that goes on. Getting optimization of the beams over the full field of view, and doing bore site rotations to cancel some of the systematics. And this would use a TMA, a three-mirror anastigmat design. The small area telescopes, again, is building on the proven designs that we heard of in Clem's talk yesterday, the BICEP Keck designs, and basically multiplying that to more small aperture telescopes. The focal plane, again, we're talking about half a million detectors over a broad range of frequencies, color-coded here. And again, you're talking about 100,000 detectors just in the small aperture telescopes. So again, we're mapping over these many frequency bands in order to be able to robustly remove the foreground signatures. So there's been a lot of improvement in the technologies. As I say, it's no dramatically new technology. It's basically optimizing technologies that we have. The detector noise is pretty much limited by the photon statistics, and that's why you need to drive to more detectors, up to this 500,000 detectors. The technology is mature. It's a question of fabricating these and doing the quality control on these, and improving things like the multiplexing as well. So the science goals, we've talked about inflation in terms of this scalar to tensor ratio R, but there's actually much more to inflation than simply detecting the gravitational waves. You can look for non-Gaussianities, which is another prediction of inflation. So this FNL factor currently is at a limit of about 5, hoping to improve that by a factor of 3-ish or so. One can look for modulations away from a simple power law a spectrum. So you look for modulations here. These are linear in the wave number. And again, improving that by about a factor of 5 or so. And then these light relics. And again, improving that again by factors of 2. And then you can look for future experiments. So for example, doing a high redshift wide field galaxy survey and cross-correlating that with CMBS4. And then eventually in the far future, things like line intensity mapping or even a stage 5 CMB survey. So there's a lot of dreams and visions out there. The US just went through what's called the visioning process, the SNOMAS process, and this figure comes from that. So we're talking about building things in the next decade, but we're keeping our eyes on what you would want to do in the future as well. The idea of building a CMB-S4, a stage 4 experiment, has received a lot of support within the community, gone through quite a number of reviews already. National Academy of Sciences report talking about NSF investments in Antarctic research, the decadal survey in the US, the National Academy's report Astro 2020, and then the NSF Physics and Department of Energy reports, the SNOMAS process, saying basically our top priority is to complete construction of CMBS4 was the community assessment. And then the agencies have to figure out, okay, how do we get the budgets to go ahead and do that? Again, it's an international experiment. There's a lot of institutions from the US, but also from Europe, from Asia, Australia, from around the world. There's a lot of enthusiasm on going after this really wide range of science. So to sum up, you're of course, trying to find the highest energy scales, these 10 to the 16th GeV energy scales where inflation might happen, but also going after the rich array of physics since then. What is the dark sector looking like? Are there more than 3 neutrinos? Are there axions? Are there isocurvature modes and so forth? Constraining the masses of the neutrinos, very complementary to the experiments such as Katrin in the laboratory, and getting insights through things like the Sunyaev-Zeldovich effect into how is matter and electrons and baryons distributed in the universe. A lot of very good complementarity in the cross correlations. And then this completely new discovery space for what transients are doing in the millimeter sky. So we're basically scaling up mature technology. We're not trying to do something that we don't know how to do. We're basically just taking what we currently have and taking it to the next level. And so it's really going to impact everything from fundamental physics to traditional astronomy. And we have a collaboration put together, as you've seen, from international across the world. And we're very much looking forward to going forward and building the experiment. Thank you.
Questions for Eric?
So can CMB S4 or maybe S5 tell us anything about baryogenesis?
To the extent that it can go after that and effective, so that can tell you something about phase transitions in the Euler universe. And so to the extent that you can tie that to some specific model of baryogenesis, it will at least give you, I think, hints in the right direction. But I won't be so bold as to say it will nail it down.
Eric, thanks for the nice talk. Could you elaborate a bit more about the cross correlation with the DESI or other like looping service, because you are looking to very different frequency, right? So
that's right, but you're still going after the same matter distribution. So you're looking at the density field either as traced by galaxies or as traced through things like the CMB lensing, the Sunyaev-Zeldovich effects, and so forth. Again, you have DESI with 14,000 square degrees. You're going to have Rubin with 14, 15,000 square degrees, and you have that overlap with the Chilean site telescopes. And so all of there used to be only sort of 2 Sunyaev-Zeldovich effects, and now there's at least half a dozen ones talking about various types of velocities along the line of sight, perpendicular to the line of sight, rotational motions, and so forth. We're going to learn a lot about the baryonic physics within clusters within the intergalactic medium. So I think that cross correlations, anytime you're talking about cross correlating over 15, 20,000 square degrees, there's just so many modes there, you're going to learn a huge amount about that.